Hello everyone, my name is Raghuram and my topic today is molecular dynamic simulation of sodium polystyrene sulfonate in a mixture of water and butanediol. I'm from a Department of Metallurgy and Materials Engineering from IIT Madras. NAPS is a very important polymer and it is used for medical as well as sensor applications. In medicines, it's used for treatment of hyperkalemia, but there are also adverse effects while using this NAPSS for medicines. And it is of vital importance to understand how NAPSS behaves in aqueous medium, and that will help us improve the systems, both in sensors as well as in medical applications. This is a turn-in-a-blend behavior of NAPSS, butanediol and water, where butanediol is a non-solvent and water is a solvent. Here we can see that as NAPSS concentration reduces, it takes more butanediol to have to get the cloud point, to achieve the cloud point precipitation, and that's most likely because of some kind of interaction where butanediol is replacing water molecules, just as we can see in this keep image. So we are starting our molecular dynamics simulation from this step. And why molecular dynamics simulation? Because it helps us understand the mechanisms in time and length scales. These are impossible to access in experiments. In our simulation setup, we are using LAMMPS for molecular dynamics simulation. The NAPSS is designed in both united atom as well as fully atomistic approach. United atom approach is used for the backbone, and then fully atomistic for the phenyl pendant ring. The TIP3P with Shea constant was used to define water molecules, and trap united atom phosphate to define butanediol. The initial setup was energy minimized with conjugate gradient method in LAMPS, and then atomic overlaps were removed using LJ salt potential. Salt potential has two parts. One is LJ and another is electrostatic interactions. The total energy of the system is given by the sum of all these bonded and non-bonded interactions, where bonded interaction are defined using Van der Waals energy term, R, which is the distance between the two atoms, Van der Waals radius. This is for Van der Waals Lennard-Jones interactions, and then Qi and Qj are atomic charges, which are used to calculate long-range electrostatic interactions. The bonded interactions are calculated using a mix of harmonic potential as well as Fourier term for dihedral for NAPSS. We are using completely isotactic NAPSS, so we are using Micropus. This is the radius of gyration resource. Here we can see that the initial state is totally stretched, but as we apply salt potential, it is come out somewhat relaxed. And then when we remove the salt potential and apply the axial potential, then we see an actual RG value. And once this chain is equilibrated, we can take it to the next steps. Here we see the RG versus chain length. The relationship is mostly linear. That's because two things. One, the NAPSS is totally isotactic, and two, it is completely sulfonated, meaning that every adjacent monomer has an SO3 minus an Na plus ion, and that electrostatic interaction is going to keep the polymer chain totally stretched. Unless we see some slight bending at a very high N values, but we are not exploring N values beyond N500. And taking the equilibrated NAPSS from a single chain, we are then adding butanediol and water. Energy minimized molecules are then used to construct a dense simulation box with a density of 1 gram per cc. Then the simulation box density is slightly adjusted with NPT ensemble. Then after this equilibration, we are using NVT ensemble for a final run. So our simulation has run till this point, and beyond this point, we are planning to do entropy calculations for solvent and non-solvent molecules using the LAMMPS compute command, and then the chi interaction parameter and hydrogen bonding to quantification of hydrogen bonding to determine the extent at which butanediol and NAPSS interacts. In future work, we are planning to extend these simulations to longer time scales and longer N values. We are also planning to compute potentials of beam force to calculate the TMF required for complex formation between NAPSS and butanediol. In conclusion, we conclude that NAPSS is a very rigid, especially in aqueous environment as well as in vacuum, within the N value of N less than 500. We would like to acknowledge PG Senapati Center for Computing Resource for giving us the opportunity to run our simulations in HPCE and ICSR because we have done this project using these two project grants. Thank you.